Hello everyone, welcome to second unit of analog microelectronic circuits. In this unit, we'll discuss about another major three-terminal device, bipolar junction transistors. So in the last unit, we were discussing about MOSFET as a three-terminal device with the terminal source, drain and gate. We have looked at how to bias MOSFET, the different regions of operation, DC problems related to MOSFET, small signal equivalent circuit, and how to use MOSFET as an amplifier. Similarly, in this unit, we'll consider BJT, the three-terminal device. Since there are three terminals, this BJT can be used to realize a current source. And this property or this characteristics is further utilized to use BJT as an amplifier that we'll discuss in the coming lectures. So as you all know, BJT it is invented in 1948 in Bell Laboratories. Since then, it was a device of choice for both discrete electronic circuits as well as integrated circuits. So BJT was a device of choice for both discrete and integrated circuits. Even though the concept of MOSFET was there before BJT, MOSFET became popular only in late 2000s. So only after 2000, MOSFET became a most widely used device. MOSFET became popular, and CMOS technology was used widely in integrated circuits. Nevertheless, BJT remains as a significant device even today. In certain applications, like BJT is significant in certain applications, especially in analog circuits and in the design of RF circuits for wireless applications as well. RF circuits for wireless applications. So that is basically due to because of two important important features of this bipolar technology is high speed, high frequency of operation, and high current driving capability. And another thing what I want to mention here is there is one more technology called as bi-CMOS technology, which is made by combining the features of both bipolar junction transistors and CMOS technology. We call it as bi-CMOS technology. So the idea is to combine the advantages of both the technologies, combine the features or the advantages of both technologies. So when that is done, this bi-CMOS technology is having properties of CMOS like low power, then high input impedance. Those properties are there, and this bi-CMOS technology also has the property of a bipolar technology, which is very high frequency of operation as well as high current driving capability. So in short, you can say even though MOSFET and CMOS technology is popular, BJT is still a significant device, especially for analog and RF circuits. So that is the whole idea why we are discussing about bipolar junction transistors in this unit. Now, if I look at the name of the device, bipolar junction transistor, the name suggests that the device is bipolar, meaning that in this device the current conduction is by both charge carriers, that is by majority and minority charge carriers, or both charge carriers. It mean that electrons and holes. We'll shortly look at the structure of the bipolar junction device, where we can see that the current in a BJT or a bipolar junction transistor constituted by both the charge carriers, electrons and holes, which is in contrast with the unipolar device what we have discussed in the previous unit, which is MOSFET, where the current conduction is only by one type of charge carriers, either holes or electrons, for P MOSFET as well as N MOSFET. Right, so that is all about the introduction to BJT. So in this unit, we'll look at these topics. We'll start by looking at the device structure. There are two types of bipolar devices, PNP and NPN transistors. The physical operation of that. We look at the characteristics, DC biasing, small signal models, and amplifier configurations. So these are the topics what we'll be discussing in the coming lectures. So to start with, we'll look at the device structure. So the structure might be familiar to you in the previous course. We'll have a quick review of the structure. We can represent the structure of a BJT with three regions. There are three regions in the structure, and as the the three regions are named as emitter, base, and collector. The three regions are named as emitter, base, and collector. So we'll mark like this: emitter region, base region, and collector region. So this is emitter, this is base, and this is collector. Now this bipolar junction transistor, or BJT, is having two PN junctions. So depending on how we choose the emitter, base, and collector region, we can have either an NPN structure or a PNP structure. That means the emitter is N, base is P, and the collector is N. This will give an NPN transistor. In the other way, if I start emitter with a P, base with an N, and a collector with a P, that gives you a PNP transistor. So these are the three regions, and the terminals are metal contacts are taken from all the three regions: emitter, base, and collector region. Now since there are two junctions, so we can identify the junctions as there are two junctions in the structure. One is an emitter base junction, and the other one is a collector base junction. This is the structure of a bipolar junction transistor. There are two junctions here. So this is an emitter base junction, and you have a collector base junction. Now we know that when you have a PN junction, we can bias a PN junction in two ways. So if there is a PN junction, I can bias in two ways. One is forward bias the PN junction and reverse bias the PN junction. So since we have two junctions here, we can bias in four different ways. That will give you corresponding modes of operation. So I'll consider emitter base junction and collector base junction, and I'll try to bias these two junctions in four different ways. First being, I'll make a emitter base junction forward bias and collector base junction reverse bias. Whenever we do emitter base forward and collector base reverse, we call this mode of operation as active mode of operation. We'll see shortly how in active mode of operation transistor works. And if you look at the typical application of this mode, in active mode, BJT is used as an amplifier. This is used as an amplifier. Now I can keep emitter based junction still in forward, and if I make collector based junction also forward, this mode is known as saturation mode. Saturation. And in the other way, if I keep emitter based junction reverse and collector based junction also reverse, we call this mode as cutoff mode. So if I look at the saturation mode where both junctions are forward biased, the device simply act as a close switch. So here this mode device act as a switch because both the junctions are forward biased, close switch, and when both junctions are reverse biased, it act as a open switch. So these two regions together can be utilized for switching applications. And finally, one more combination is possible where I can reverse bias emitter based junction and forward bias collector based junction, which is exactly the inverse of this active mode, and we call this mode of operation as inverse active or reverse active. So now if the mode of operation is inverse to the active, the application also should be that way. So if I use a transistor in this mode, generally it is not used, but we can see that it will give a performance of an attenuator. But generally this is not used because attenuation is basically done using passive elements. No need to use a active device, bias it and use it as an attenuator. But using passive elements only we can get attenuation. So this mode is not generally used, but it is required to understand the operation of transistor. So as I mentioned before, bipolar is the device is called as bipolar because charge carriers are of both polarities, that is both electrons and holes participate in current conduction, right? So this is all about the structure and the ways of biasing the transistor, and also the different modes of operation and application. Now let's see the operation of an NPN transistor. So let's discuss the operation of NPN transistor in active mode. NPN transistor in active mode, because even we are discussing or we are this course is all about learning how to design amplifiers using different devices. So here since I mentioned that BJTs are used as amplifiers in active mode, we'll discuss about the active mode of operation, and I'm considering NPN transistor for the discussion purpose, right? So I'll take the structure what I have drawn before, the same structure I'll consider, where you have an N region, you have a P region, and you have another N region. Yeah, so this is the structure of an NPN transistor. So I think the reason for showing P or the base as very short, collector as very long is obvious. Yeah, so these are the three terminals. Yeah, so just want to mention here that emitter is heavily doped. The structure is doped in such that the emitter is heavily doped, where your base is lightly doped and your collector is moderately doped. So this is the doping level, the number of impurities, the concentration of impurities. Now we'll look at the actual transistor structure also, so that this will be clear why emitter is small compared to collector. All those things will become very obvious when we look at the structure. Now So since I mentioned that we'll be looking the operation of NPN transistor in active mode, this is an NPN transistor, this is emitter, base and collector. So I need to forward bias this junction should be forward bias, and this junction should be reverse bias. Now to forward bias this junction, N should be connected to negative and this base should be connected to positive. So that will make this junction forward bias. Now this is plus and this is minus, so I'll mark this voltage as VBE. VB is positive, VB is positive, VEB is negative because N should be connected to N. This is at this end, and the other end should make this collector base junction reverse bias. That means N should be connected to positive to reverse bias this junction, and P should be connected to negative. So this is plus minus, and I'll mark this as VCB, where VCB is a positive value to reverse bias collector base junction. Right. Now we look at this junction. In this emitter base junction, so since this emitter base junction is forward bias, since this is forward bias, so I'll not be looking at all the minority carriers or all the we'll not be looking into the details of the current. So we'll be quickly reviewing the operation so that we can go ahead with the other topics, right? Yeah, but we'll try to understand the operation with this short discussion. Now when your emitter base junction is forward bias, we know that if a PN junction is forward bias, current will flow through this junction. So you can see that this junction is forward bias. So here we have electrons will actually flow to this, so I'll call this as injected electrons here, and we have holes here. Holes will move from this end to this end, so this is actually your injected holes, right? Now yeah, so with this I want to mention one more thing, the current direction. So conventionally the current direction is taken as the direction of hole flow, right? Maybe even in a MOSFET we have seen the same thing. The actual direction of current is taken opposite to the electron current flow. So since the electrons are flowing from N to P this direction, the actual current direction will be the opposite. So I'll mark emitter current outside like this, and I'll mark this as IE, right? Now once emitter current, if it is flowing outside, okay, we can see here now the base current is, or from here this P region, holes are actually flowing in this direction, so the current direction should be the same as hole flow. So this will be our base current, and finally here, yeah, we'll come to the collector flow. Yeah, we look at this junction. So injected electrons will be injected from emitter to base. But now this injected electrons, when it reaches base, that becomes minority carriers in base, right? Because base is P region, so these electrons in base is minority carriers. These injected electrons are minority carriers in base. And since there are free holes here, some of the electrons will recombine with holes, some electrons will recombine, but since the base is thin, the base region is made very thin, the portion of electrons which are lost in recombination is very small. So even though and the emitter is heavily doped, so a huge amount of electrons will reach base, few will be recombined, but few will be recombined there, but since the base region is very thin, the number of electrons lost in recombination is small. So injected electrons are minority carriers in base, few electrons will be recombined. Why only few? Because base is thin, right? Now now we look at the collector base junction. So electrons reached here, few are recombined. So what will happen to these electrons? To understand that, we look at the other junction, which is the collector base junction. So this collector base junction is basically reverse biased. So this junction is reverse biased. Now, so since this junction is reverse biased, there will be a small depletion region across this PN junction. Now, the electrons, the injected electrons from emitter after recombination will reach the boundary. Will reach the boundary of this collector base depletion region, because there is a depletion region because of the reverse bias of the collector base junction. Now, if you look at the collector region is N, but collector is connected to a high positive value. The collector junction is this junction is reverse bias, but the collector is connected to a high positive. So since collector is made more positive than base, the successful electrons, the electrons which has reached the collector base junction, will be swept across the collector base junction depletion region into the collector. So electrons are coming from this emitter to base. Few are recombined here, but collector is having a high positive potential here. So the successful electrons which reach this barrier, this depletion region, will be swept to this collector, or the collector will collect most of the electrons which has started from emitter. Few will be recombined in the base. So this will constitute the collector current. Right. So in short, I'll say emitter base junction is forward bias. So electrons will be injected from emitter to base. Base is very thin, so few electrons will be recombined, but these electrons will be further attracted by the positive potential which is connected to the collector. So the electrons will be swept across this depletion region, and the electrons will reach the collector, which constitute the collector current. Now electrons are flowing in this direction, so collector current will be in the opposite direction. So this is IC, right? So if I look at the total current in a PNP, in a transistor, the total current is, emitter current will be equal to base current plus collector current. IE is equal to IB plus IC, right? Now one more thing we can write here. So here the collector current can, so all these currents can be expressed in terms of diode current. So if I have a diode, say if you have a diode, the current through the diode is expressed as ID is equal to IS into e to the power VD by eta VT. It is so generally we write this as -1, or approximately we write this as IS into e to the power VD by eta VT, where VT is volt equivalent of temperature, IS is called saturation current. So saturation current again depends on many other things. So I can say one thing: saturation current depends on the area of the junction. I'll write it is proportional to the area of the junction and inversely proportional to width of the junction. So maybe this I'll tell with respect to transistor. So the IS is saturation current. Now if I write the current that reach the, if I write the expression, if I use the diode expression for collector current, I can write collector current as IC is equal to IS into e to the power of VBE by eta VT or VT. I can write IC as this. So that is the current that reached the collector, because again the current at the collector base junction is diode current that depends on saturation and as well as the voltage, the base emitter voltage which is applied here, right? Generally we can see that magnitude of this IC, because if you look at this junction, this magnitude of this collector current is independent of this VCB. As long as this collector is more positive, That means this VCB voltage is actually attracting, which is actually pulling or sweeping the electrons across the PN junction, the reverse bias PN junction. But we cannot see a significant increase in collector current with respect to VCB. Or as of now, I'll say collector current, the magnitude of collector current is independent of VCB. Still, but there is an early effect that we'll see little later. Okay. So this is all about the operation of transistor. So with this, I just want to write few expressions here. The very first expression is the total current, emitter current is equal to base current plus collector current. That expression we know. And the other known expressions are collector current can be expressed in terms of emitter current by using a factor called alpha. We call it as current gain. Collector can be expressed in terms of base current by a factor called beta. So now when I use this over here, when I apply this IC over here, now IE can be written as IB plus beta IB, or I can write IE as beta plus 1 IB. So these three relations are useful relations to solve even numericals with respect to bipolar junction transistor. So this is important. Total current will be sum of base and collector current. Then collector current is alpha times IE, and collector current is beta times IB. So these four expressions are important. Now with the same thing, so I mentioned IC as IS into e to the power of VBE by eta VT, or simply VT. If IC is this, how can I write IE? Because IE is IC by alpha, right? IC by alpha. So it is IS by alpha into e to the power of VBE by VT. So which, so alpha is actually, if you look at the numerical value of alpha, alpha is a quantity which is lesser than 1. So IE will be slightly more than IC, right? So that is obvious from these two relations. In certain times, if I approximate alpha equal to 1, IE is equal to IC. If alpha is equal to 1, IE is equal to IC. Again, that is obvious from this relation, right? Yeah, so these things are very important. And one more observation, what I want to make here is the relation between alpha and beta. All these are defined as current gains in different configurations. So alpha is called as common base current gain, and this beta is known as common emitter current gain. Now the relation between alpha and beta is alpha by 1 minus alpha is beta, or alpha can be written as beta by beta plus 1. So a very important observation what I want to make here is, if say alpha value is 0.980, if you calculate the corresponding beta, you will get beta as 50. Now if I vary alpha by a very small quantity, say from 0.980 to 0.993, the variation is very small, from 0.980 to 0.993, but the variation in beta is actually very large. Beta will become 150. So when alpha varies by a very small amount, beta actually varies by a very large amount. So the relation between alpha and beta is in such a way that the variation in alpha is small, if the variation in alpha is small, but the variation in beta is very huge, right? So even this we'll see when we look at the characteristics. Now just I want to show the structure of a BJT. Like MOSFET, BJT can be considered as an N, a P, another end, where this is your emitter terminal, this is your base terminal, and this is your collector terminal. Now, in contrast to MOSFET, this BJT is not a symmetrical device. It's not a symmetrical device. So when we discussed MOSFET, we stated that MOSFET is symmetrical. Its collector and emitter terminals can be interchanged. But here we cannot do that. Now if I interchange, if emitter and collector are interchanged in a BJT, say for active mode of operation, we want to use transistor as an amplifier, and we are specifically looking at biasing emitter base forward and collector base reverse. But if emitter and collector are interchanged, the mode of operation becomes reverse active instead of active, right? So we cannot do that because the device is not not a symmetrical device. Now let us see the symbol of BJT. So BJT symbol, an NPN transistor is denoted by this symbol, where this arrow mark represents emitter, this is the base terminal, and this is the collector terminal. Now arrow mark is given to identify the current direction. So since arrow mark is outside, emitter current is flowing outside, IE. So the other two currents are flowing in, IB and IC. Because this relation is valid, IE is equal to IB plus IC. This is a NPN BJT. Now for a PNP BJT, the symbol remains same with the only difference of arrow mark inside. So again, arrow mark shows emitter, this is base and this is collector. Since arrow mark is inside, emitter current flows in, so base current and collector current flows out. Again, this relation holds good. IE is equal to IB plus IC. Right. Now we'll quickly look at the characteristics of transistor. If I'm using this BJT, so I can use BJT in different modes, right? What are the different modes? There are 3 terminals, so I can make 3 terminals common, and I can connect input to one end and output to the other end. So quickly I'll say, if I'm keeping base common, we call this as common base configuration. Now if I'm keeping emitter common, call this as common emitter configuration. And if I'm keeping collector common, we call this as common collector. Right. So these are the 3 configurations. Now if base is common, input will be applied here and output will be taken from here. If it is common emitter, input will be applied between base and emitter, output will be taken between collector and emitter. Now if it is common collector, so I'll just draw this structure in the other way. Where I'll make this collector terminal common for the input signal. So input will be applied to base, where collector is the common point. Output is taken from emitter. Output will be taken from emitter, where collector will be the common point. So we look at specifically we look at the configurations. Right now, quickly we'll see the characteristics also, because just want to review what you have done in your previous semester. So say I'm looking at common base configuration. Common base configuration where so this is your common base configuration, right? So emitter current is this, base current is this, and collector current is this. Now if we want to bias this common base configuration, this is N, P and N. So N should be connected to negative and this should be connected to positive. So I'll mark this as VBE. Now output side, N should be connected to positive, this should be connected to negative. So this I call it as again VCB. Now input characteristics of any configuration is, input chara is actually the variation of input voltage versus input current. So in this case input voltage is VBE and input current is IE, which is for a common base configuration. Right now you can see that emitter base junction is forward bias, so the input chara of this configuration will be same as that of a diode. So after the cut-in voltage, or after the cut-in voltage, the junction current will increase, and we can actually plot this for different values of VCBs. Different values of VCBs. Now similarly we'll write the output characteristics of the transistor. So the since the input side is a forward bias PN junction, the chara resembles same as that of a diode chara. Now output chara, we'll plot output voltage. Output voltage here is VCB versus output current is IC. Now the configuration is common base. So how this input and output currents are related? Now this output current will come, this IC current will flow only if you have an emitter current. Since emitter base junction is forward bias, this is forward bias, emitter current is there. Now emitter current is related to collector current as alpha IE. That means your IC and IE are almost same, almost equal, right? Now how to draw this chara? If you look at the collector base voltage, as long as this VCB or as long as this collector base junction is reverse biased, I'll write this here, as long as collector base junction is reverse biased, if this junction is reverse biased, what will happen? IC will be flowing, I'll write IC will be constant because nothing is there to vary IC, or IC will be equal to alpha IE. Now you should not get the doubt how a current flows when this junction is reverse biased. So that is what we discussed here in this structure. So this junction is reverse biased, this is forward biased. The injected electrons will reach base, but base is very thin and narrow. Very few recombination will happen, but from the collector side you have actually a very high positive potential available. So that will actually attract the electrons, because electrons will be attracted to positive polarity and the collector is connected to very high positive polarity. So this will definitely sweep the electrons from base to collector, crossing the barrier at the collector base junction. So that will constitute the collector current. So as long as you have a high reverse bias, or as long as this collector base junction is reverse bias, then only I will get a positive potential here which can attract the electrons. So as long as this remains, collector current will flow. So that is what I want to write here. As long as collector base junction is reverse bias, IC will be constant. That means if you have an IE, you will definitely have an IC. So this is IC. I will write IC is equal to alpha IE. Now when this current will change, or when does this collector current drops, right? That means if at all this junction turns forward bias, If this junction turns forward bias, there is no high positive potential to attract the electrons, so the electrons will not cross the collector base junction and your collector current will actually drops to 0. Right. So what is that point? Maybe I'll consider, see, when VCB equal to 0, so this VCB is reduced, so this is the 0 point. So when your collector base junction voltage is reduced, so this is your collector, this is your base, this voltages keep on reducing. Now say if your VCB is equal to 0, whether for VCB equal to 0 the junction will be forward biased. You have a PN junction. If this voltage is 0, will the junction be forward biased? No, this junction will not be forward biased. That means even for VCB 0, the junction is still reverse biased, and if the junction is reverse biased, you can actually expect a current. That means this current will be IC will be equal to alpha I even for VCB equal to 0. Now at what voltage will this junction becomes forward biased? So generally, this you make a note. Generally a PN junction, I'll write it here. A PN junction will not be forward biased until the forward voltage exceeds a particular value, exceeds approximately 0.5 volt. This is observed. Now in the case of MOSFET, it is obvious that you have a threshold voltage. MOSFET, we always talk about a threshold voltage VT, and only when your VGS crosses VT, MOSFET turns on. Similarly, for a PN junction, the junction will not be forward biased until and unless it reaches a particular forward voltage. Typically that voltage is 0.5. That means if you have a voltage equal to 0.4 also, the junction is not forward biased, right? So the clear point here is a PN junction will not be forward biased until and unless it reaches a particular voltage. That means for a 0, for this PN junction, if you apply a 0 voltage, this is not forward biased until if you give a 0.5, this will turn forward bias, right? That means till 0.4 the PN junction is reverse biased till 0.4. So the same thing I am taking here. If I look at this PN junction, for VCB equal to 0, the junction is not forward biased. So when your VCB equal to till VCB equal to 0.5, when I say VCB equal to 0.5, your collector has a higher potential. So VCB should be equal to minus 0.5, right? VCB will reduce to 0, then VCB will increase in the reverse direction. So till VCB crosses say some minus 0.4, you will actually get a current, and after that when your VCB equals minus 0.5, when VCB equal minus 0.5, your junction actually turns forward bias. That means if the junction turns forward bias, emitter current will not be attracted to the collector, or I can say the current will easily drop to 0, right? So you can actually mark till this point, till the junction turns forward bias, the region is active. That is why we generally mark the output carrier of a common base in this way, and beyond this the device is in saturation, right? So beyond this is in saturation, so till that point it is in active region. So this is actually the output carrier of a common base configuration. Now similarly, if I look at common emitter characteristics, we'll quickly look at that also. Common emitter. So you have the transistor here. Yeah, this is NPN. So this junction should be forward biased. So this is your VBE. This junction should be reverse biased. This is your VCE. Right. Now here also input carrier remains same because you have a emitter based junction. It is emitter based junction is forward bias, so the input carrier remains same as that of a diode carrier. And input carrier is drawn between VBE and input current. Input current is base here. If I mark the current direction, this is IE, so this is IB and this is IC. Now if you look at the output carrier, so output carrier is drawn at between IC and VCE. Now so now here the voltage what I have connected is VCE, but the junction reverse biasing depends on the voltage VCB. So this is C and this is B. So this voltage decides, VCB voltage decides whether the junction is forward bias or reverse bias, but we are not connecting directly a voltage between collector and base. So collector base junction is forward biased by the effective voltages applied to base at the base emitter side and collector at the collector emitter side. Now if you look at the carrier of this, so I'll consider the previous case. So we know that till VCB equal to minus 0.4, the PN junction is reverse bias, and when the VCB crosses minus 0.4, the junction will turn on, or the junction becomes forward biased. Now, so this I am keeping. Now I am considering another value where VBE equal to 0.7. Just to plot this graph, so the output carrier is drawn for different values of IB. Now if there is one particular value of IB, there will be some VB value. So I am assuming that VB is 0.7. Now the voltages applied are VB and VCE. Now when you have low values of VCE, at low values of VCE, if your VC goes less than VB, if your VC goes less than VB by more than 0.4, that is what I mentioned here, right? If a VC goes less than VB by 0.4, what will happen? Collector base junction will become forward bias, and that leads to transistor will enter into saturation region, right? Now here in this case, when I consider VB as 0.7, for VC equal to 0.3, your VCB voltage becomes minus 0.4. So for voltages less than VC equal to 0.3, transistor turns into saturation region and the current will actually drop. So say if you have a current here, when it reaches 0.3, current will actually drop to 0. Now compared to common base carrier, here your collector current is equal to alpha times IE, but here you have input current as IB, and we know the relation between IC and IB is IC is beta times IB. If you look at the characteristics, you can see a little more slope compared to your common base configuration. So this is due to the phenomena called base width modulation that we will discuss shortly. Base width modulation, or we call this as early effect. So two things what I want to conclude here is, when I look at the characteristics of common base and common emitter, input carrier remains same because input side is a PN junction. When it is forward biased, the carrier looks same as a diode carrier. But if you look at the output carrier of common base, you have the collector base voltage, and for a zero collector base voltage, this junction will not turn forward bias. The junction is not becoming forward bias. A collector current will flow. That means the collector current will flow even for a zero VCB, and even if your VCB is less than 0 till VCB equal to minus 0.4, you can expect a current. After that, your current will actually reduce to 0. So why current is reducing to 0 is because here the transistor enters saturation region. In saturation region, there is no higher positive voltage to sweep the electrons, right? So that is because of the reason that in MOSFET you have a obvious threshold voltage, but generally in PN junction, a junction will be forward biased only if a minimum voltage of 0.5 is required, irrespective of the material type. Similarly, in a common emitter carrier, the same VCB voltage I am keeping as minus 0.4. Now if my VB is 0.7, when your VC is less than 0.3, your current will actually start falling. So this is your active region, and this is your saturation region. So maybe these things you would have seen in your previous courses, right? So this lecture I am just concluding with the characteristics. In the next lecture we'll start looking at DC biasing, small signal models, and amplifier configurations. So this is an introduction lecture. So understanding these concepts and the characteristics will actually make your